All right, as we make our way to the next unit of exploring the properties of angles and triangles and polygons as well, we are going to be doing a little side unit on some logical thinking. So this is in chapter 1 in your textbook. And so we are going to be exploring just how we follow the lines of logical thinking. And we'll be looking at how we make conjectures, what a conjecture is. And we'll be looking at two types of reasoning, in two types of logical reasoning. The first being inductive reasoning, and the second being deductive reasoning. We will also explore how to disprove a conjecture through counterexamples. So today's lesson, we are going to be exploring how to make a conjecture. So a conjecture is a general conclusion or a guess about something, so an event or some information that is based on limited evidence and is not yet proved. So a conjecture is not a conclusion. It is not, like it's a general conclusion, but it's not proved. So conjectures generally are based on inductive reasoning. And so inductive reasoning is when we draw a general conclusion by observing patterns and properties in examples. So that's extremely important. Inductive reasoning involves examples. So we start with gathering information, looking for patterns, and then we put together a general conclusion based upon those patterns. So for example, let's take a look here. We are adding two types of integers, odd integers. So you'll notice we have 1 plus 1, 1 plus 3, 3 plus 5, 7 plus 9. So we are going to determine, based on these examples, 1 plus 1, 1 plus 3, 3 plus 5, 7 plus 9, what the sum would be. And can we make a general conclusion about the sum? So 1 plus 1 is 2. 1 plus 3 is 4. 3 plus 5 is 8. And 7 plus 9 is 16. If we looked at another example, let's say we had 17 plus, I don't know, let's say 11, the answer would be 28. So we have some different examples, okay? We're going to use now inductive reasoning to come up with a general conclusion. So what conjecture can we make about the sum of two odd integers? So my conjecture is that the sum of two odd integers is always an even number. Certainly from our examples, it's showing that 2, 4, 8, 16, 28, those are all even numbers. So our general conclusion, our conjecture, is that when we add two odd integers, we will always have an even number. So that is kind of how we state a conjecture. So my conjecture is ... something is always going to happen. So we want to start with my conjecture, and we want to have the word always in there. All right. So the conjecture could be the sum of two odd integers will always be an even integer. All right. And we can even change number to integer. And we just followed some inductive reasoning, which means that we started with some examples, gathered data, and we found patterns. And that's pretty much what inductive reasoning is. And that's kind of what we do to follow inductive reasoning to put together a conjecture. Okay, so we'll look at another example here. We are multiplying, okay, numbers, you'll notice, always by 10. So 3 times 10, 14 times 10, and negative 867 times 10. So 3 times 10 is 30. 14 times 10 is 140. And negative 867 times 10 is negative 8,670. So what conjecture can we make when we multiply a value and 10? Well, if we look, our initial value is 3 and the product is 30. So it looks like we've added a 0. Our initial value is 14 and we've added a 0. Our initial value is negative 867 and we added a 0. And notice that the 0 is in the ones position. So it looks like whenever you multiply a value and 10, you simply add 0 to the ones position of that value. And you can state a conjecture in different ways. So how one person words might be different than another person words, but you should always start with, you should always start a conjecture with my conjecture. And then we are going to state our general conclusion. So again, our general conclusion is that when we multiply a number by 10, we're always adding a 0 to the ones position. So my conjecture is that the product of a value and 10 always has an extra 0 added to the ones position. And there's different ways we could state it, but that's kind of what it is. All right, so I hope that kind of makes sense to you about how we state a conjecture. Again, the key word is we start with my conjecture. Sorry, my conjecture is, okay, put that all together. Okay, so we kind of repeat what we are doing. So we're multiplying a product, or sorry, we're multiplying a value in 10. And then we have the word always in there as to what our outcome is. So our conclusion is that we're always going to add an extra 0 to the ones position when we multiply a value in 10. So that is an example, another example of a conjecture. So again, we'll move on. We're just going to look at different examples here. So we have a figure, triangle, and you'll notice that we are consecutively adding new triangles in different levels to the shape. And we are going to make a conjecture about the number of triangles in figure 10. So we are going to just fill in the table about the number of triangles in each figure and gather some information. So figure 1 has 1 triangle. Figure 2 has 4 triangles. Figure 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, has 9 triangles. So we need to find a pattern. What we could do is draw figure 4, 5, 6, 7, 8, and 9, and then 10. But that would take a long time. We're going to see if we can identify a pattern based on the number of triangles in the figure as per what's happening from each figure to the next. So figure 1 has 1 triangle, figure 2 has 4, figure 3 has 9 triangles. So kind of what's going on here, the general pattern is that we are taking the figure number and we are squaring it to get the number of triangles. Let's test that. So figure 1, 1 squared equals 1, matches. Figure 2 squared equals 4. Well, that matches. And last but not least, figure 3, we square it, that equals 9, and that matches. So if that's our general pattern, the conjecture that we could make about the number of triangles in figure 10, my conjecture is that figure 10 in this series, or sorry, in this sequence, will always have, so we can figure that out. figure 10. We'll square figure 10 and we get 100. 10 squared is 100. So my conjecture is that figure 10 in the sequence will always have 100 triangles. That is our conjecture about that. Okay. We are going to move on now, and we're going to be just going to do some inductive reasoning in some different examples to find out any kind of general pattern, and then make a general observation, i.e. make a conjecture about what we're tasked to do. So here we're looking at the product of two odd integers. So to do inductive reasoning, we have to gather data. So we have to start with doing the task that's being told to us, and that is multiply product two odd integers. So we have to pick any two odd integers and multiply them. So an easy one would be 1 times 3. So 1 times 3 is 3. Another one, we can go 5 times 9, 45. You can go negative 11 times 3, that's negative 33. And we'll do another one. We'll do negative 7 times negative 3. That equals positive 21. So we need to focus in on the product. And is there a general pattern going on? Okay, so the general pattern here, we've got 3, 45, negative 33, and 21. We've got negatives, we've got positives, that's fine, but look at the type of number. You multiply two odds and the product is odd. 45 is odd, negative 33 is odd, and 21 is odd. So based on this data from the examples that I chose, okay, my conjecture is that the product of two odd integers is always an odd integer. That's valid based on the data I collected. So I use inductive reasoning to make a conjecture. So we'll move on. Use inductive reasoning to make a conjecture about the difference between consecutive perfect squares. So consecutive means in a row and a perfect square. Remember from grade 9 math, perfect square is a number that has a whole number square root. So for example, 9 would be a perfect square. The square root of 9 is 3. Okay, so that is a perfect square. All right, so we need to subtract consecutive perfect squares. So our perfect squares would be 1, 4, 9, 16, 25, for example. So we will go let's do 5 squared minus 4 squared. We can do 9 squared minus 8 squared. We'll do one more example. Always try to do 3 minimum. Let's do 3 squared minus 2 squared. Okay, so 5 squared minus 4 squared. 5 squared, that's a perfect square, 25, minus 4 squared, 16. So 25 minus 16 is 9. 9 squared is 81. Minus 8 squared is 64. Oops, 64. So that would be 17. 81 minus 64 is 17. 3 squared minus 9 squared, that's 9 minus 4 equals 5. So we've got to look at the pattern with the differences. So we've got 9, we've got 17, and we've got 5. So what do we have here? We have 9, we have 17, and we have 5. What's a pattern? Well, they're odd numbers. Sorry, they're odd integers. So the differences are all odd integers. So my conjecture is that the difference between consecutive perfect squares is always an odd integer. Okay. And there that is. So again, we're just exploring gathering data, inductive reasoning, finding a pattern, and then stating a general conclusion of that pattern. Remember having the keywords beginning with my conjecture is, okay, that whatever we were doing, so the difference between perfect squares is always, and we have that word in there, those words in there as well. Okay, use inductive reasoning to make a conjecture about the product of flipped reciprocal, which are flipped fractions. Okay, so if we have the fraction 1 over 2, then the reciprocal is flipped 2 over 1. Okay, so now we know that. We can go ahead and gather some data. Okay, so let's do 1/2 times 2 over 1. So again, multiplying fractions, we have top times top, so 1 times 2, which is 2. And bottom times bottom, 2 times 1. Actually, why don't I write it out like this? It'll go 1 times 2 over the bottom 2 times 1. And so that will be a fraction, 1 times 2, 2 over 2 times 1, 2. So 2 over 2, well, that reduces to 1. So we can try another one. Let's try 5 over 6 times the reciprocal, 6 over 5. So that will be 5 times 6 over 6 times 5. Okay, so 5 times 6 is 30 over 6 times 5, 30. So 30 over 30, well, that is also equal to 1. So we'll do one more example. We can do 4 over 5 times 5 over 4. That basically is 20 over 20. Is also equal to 1. So we have the product is always 1. That's the pattern. So my conjecture is that the product of reciprocal fractions is always equal to 1. Okay, so that is another example. And I think we'll look at our last example here. I'll just move this down. Okay, so use inductive reasoning to make a conjecture about the square of integer values containing only digits of 1. Okay, so I think we'll do the easiest. We'll go 1 squared. The next one will be 11 squared. And we'll do 111 squared. So these are digits only containing 1. So we have 1, we have 11, and we have 111. Okay. So 1 squared is equal to 1. Tab this over. 11 squared is 121. And we will look at 111 squared. So 111 squared, you get 12,321. 12,321. Okay, so is there a pattern going on here? Well, notice that if it only contains 1, the square, first of all, begins with the number 1. If it has 2 or more digits, it begins with the number 1 and it ends with the number 1. And there's 2 1s, so it is a sequence that goes 1, 2, 1. So it counts up to 2 and then back to 1. So 1, 2, 1. There's 3 1s, so it counts up to 3, 1, 2, 3, and then back down to 1. So let's try with 4. Could we make a prediction? 1,111 squared. Well, there's 4, so it would go 1, 2, 3, 4, 3, 2, 1. So that would be 1,234,321. Let's see if our conjecture is right. 1,111 squared. 1,111 squared. You get 1, 2, 3, 4, 3, 2, 1. Okay, so now it's just a matter of putting this into words. So what is our square? The square would be the number that's equal to counting up to the number of 1s in the digit and then back down. So starting at 1, counting up to the number of digits containing 1 and then back down to 1. Again, you can state it in many different ways. This might be a bit wordy. My challenge would be if you can state it more concisely, then send it off to me on an email and see if it's a bit more concise. So my conjecture is that the square of integer values, can't spell square, square of integer values containing only digits of 1 is always equal to, is always a number that starts and ends with 1 and counts up to the number of 1s in the digit or in the number being squared and back down again. So that would be one way of stating it, a bit wordy, but I am going to make you a challenge if you can make that less wordy and if you can email that to me. So we've just explored making conjectures using inductive reasoning by gathering data, finding a pattern, and then making a general conclusion. And a conjecture always starts with the words, my conjecture is that, and then it has our conclusion always has always in it. So my conjecture is that, ... always, whatever the conclusion is. So these examples are here for you. I hope they make sense. I'll upload the notes, the filled in notes to my website if you want to download it. And then the homework would be here page 12, questions 1, 2, 3, and 4, and then 7, 8, 9, 10, 11. All right, so good luck learning about conjectures and inductive reasoning.